A blower door test is used to determine the air tightness of a building enclosure's air barrier system. Air tightness is critically important to the long-term energy performance, durability, comfort, and air quality of buildings. The insulation in a building enclosure resists the flow of heat between the inside and the outside of the building and is usually in intimate contact to the building's air barrier system. The system's main purpose is to control airflow through the enclosure. However, if there is a hole in the assembly, the air can leak into or out of the building, increasing energy consumption. Uncontrolled air leakage also carries moisture which can flow through the wall and roof assemblies, condensing as the temperature drops below freezing and often gets trapped in the enclosure system. This can cause mold and rot in serious conditions. A blower door test is used to understand how much air is entering or exiting the building at a specific pressure. Some building energy certifications require specific air tightness targets such as Passive House, Energy Star, and the OBC energy codes for residential and commercial buildings. Typically, air tightness flow rates are normalized to a dimension specific to the building. In the case of commercial buildings, the flow rate at 75 pascals will be normalized to the skin surface area in liters per second per meter squared of air barrier of the system. Whereas, in smaller residential buildings, the leakage rate at 50 pascals is normalized into the conditioned volume and is measured in air changes per hour, and it represents the amount of air in a space that is fully replaced by air leakage in 1 hour. The blower door test uses a fan to blow the air into the space, pressurizing it. This forces the air within the building out of all the holes throughout the space. The fan can be reversed, depressurizing the space, which forces the air into the building from the holes. Air tightness is then determined using both the pressurization and depressurization results. When renovating buildings, it is important to understand how leaky a building is, because major energy savings can be seen when increasing the air tightness. Therefore, a blower door test will be conducted before, during, and after renovation. Broadly speaking, there are two types of air leakage tests: building envelope tests, which is where the HVAC-related openings are excluded, compared to the operational envelope test, where the building envelope and HVAC-related openings are both included in the test. The latter is often referred to as an as-is test and is used primarily in energy simulations to estimate energy consumption of buildings. The leakage rate of a building can be measured by depressurizing or pressurization, but best practice is to measure the leakage rate under both conditions and report the average. There are specific testing standards developed by various institutions, including ASTM and the US Army Corporation, that require certain things to happen during a blower door test. When conducting a blower door test, determine the volume of the house before beginning the test, because it is needed to calculate the overall air tightness. State to the client and stakeholders which test standard you are complying with when conducting the test, and bring a copy of the standard with you in case you forget something. To set up the test, the first thing that is needed is to walk around the building, ensuring that all interior partition doors are open and all exterior windows and doors are closed. This is done to make the building one zone to be tested. To adjust for air density, temperature of the outdoors and indoors is taken, as well as the wind speed and direction. Finally, barometric pressure is also measured. The next step is to put the frame together and roughly insert it into an exterior opening, usually a door frame. The frame size is adjusted by loosening and sliding the frame to fit. Tighten the knobs, leaving the cams disengaged. When roughly installing the frame within the door frame, the fit should be snug but not impossible to move. The frame is then removed and the door panel is then attached to the frame using the Velcro. Pass the green and blue tubes through the small holes at the bottom of the door panel. Place the tubes in a mailbox or a shoe to keep the tube out of the wind. Place the frame back into the door and lock it in place using the cams or latches. Attach the cross member to make sure the frame stays in place during the test. Ensure that the tubes on the outside are protected from wind gusts, so place it out of the way of the fan. It is helpful to have a second person with you to move the tubes outside, so you do not have to crawl through the fan hole in the membrane. Next, attach the manometer to the frame using the mount, and the green tube from the outside to A, and place the red tube to B. The manometer at Ryerson is the DG1000. This manometer has a setup guide as well as various measuring options. Software such as TechTite Express can be downloaded and the results can be plotted instantly. Take photographs of areas of the building that could be areas of air leakage. Place the fan onto the fan hole, ensuring that there are no gaps between the membrane and the fan. The other end of the red tube is inserted into the fan port and the fan can be plugged in. We are now ready to test. Before the test can begin, the fan should be closed and the pressure should be measured. This accounts for ambient wind and environmental conditions. This is known as the opening pressure. The rings of the fan are then removed from the fan and the fan can be started. Most tests require the building pressure to be increased to 60 or 70 pascals when pressurizing and -60 to -70 pascals when depressurizing. The fan speed can be increased using the dial until the manometer measures the building pressure recorded on side A. The pressure across the fan is measured at the specific building pressure over a 10-second average. The building pressure is then reduced by 5 pascal increments until the building pressure is at 10 pascals for most tests, or when the fan pressure drops below 25 pascals. This is when the readings become inaccurate. When this happens, ring A must be placed onto the fan. Each ring, named A, B, C, D, E, and F, reduce in size, increasing the pressure across the fan. High-performance buildings will need smaller rings, such as C, D, and possibly E if the building is extremely airtight, while leaky buildings will use the open fan and rings A. Once the test is complete and all readings have been collected at 5 pascal increments, the fan is closed again to determine the closing pressure. All pressure readings are recorded for both pressurization and depressurization tests. The results are then used to calculate the airtightness of the building.